we're going to cover longest substring without repeating characters. Given a string S, find the length of the longest substring without duplicate characters. I've hidden the examples as well as the constraints because I wanted to make sure that you can practice ambiguous prompts. This allows you to prevent yourself from making assumptions and clearly define the problem, inputs, outputs, and your understanding of the problem. Let's start off by declaring our inputs and our output for this question. So for our input, we're given a string S. And I will write unknown here because this is an ambiguous input without a lot of details other than its data type. Our outputs, they're expecting us to provide an integer, and this would be the length of longest substring without duplicates characters. All right. So now that we've pretty much put out our given onto our whiteboard, we want to start asking some clarifying questions for our unknown. The first question you can ask is, what kind of characters are we looking at for string S? So let's write that down. What kind of characters will we get in string S? Right? Will it contain symbols? Will it contain letters, uppercase, lowercase? Will it contain any numbers? These are the kind of questions you want to ask. So let's say that the interviewer told you this consists of English letters, numbers, symbols, and spaces. Now, before you ask your second clarifying question, you have to make sure that your interviewer's answer is as clear as it can get. So even if your interviewer replied telling you that it consists of English letters, numbers, symbols, and spaces, you want to ask more about English letters, right? Are we going to contain uppercase and lowercase letters? Or only one or the other? So make sure to clarify the answer if there is still some ambiguity about it. So uppercase or lowercase considered. And in the terms of duplicate characters, we want to ask, is uppercase going to be considered a duplicate if it finds the lowercase version of itself, right? Is this going to give us an output of 3 or 2, right? Is A and capital A unique, or are they considered a duplicate? Dupe or unique? So this is just one example and one question, and you see that you clearly break down the problem so you can understand better what you're trying to solve, what kind of solution you want to build. And not only that, but later on, once you've come up with a solution, how you can optimize your solution. So let's move on. Another common question you can ask is about the range of the input. So how large can string S get? How small can string S get? So what is the min and maximum amounts of characters in string S. And the interviewer will give you the answer to this. They can say that it's between 0 and 5 times 10 to the power of 4, inclusive. So as you're building these clarifying questions, you should be able to identify some of the edge cases that you'll find in your solution that you'd have to account for. For example, when they mentioned about English letters, we inferred that there's chances of uppercase, lowercase. This is an edge case of whether we should consider them as duplicates or unique in a set of string S. In the next clarifying question, we asked about the min and max, and we're given that it's between 0 and 5 times 10 to the power of 4 inclusive. So including 0 means that we can get an empty string. So we have to account for this in our edge case. Can be an empty string. And these points, right, about the duplicate unique, how we consider them, and whether or not, and for the case scenario of it being an empty string, these won't be written at the same time of the clarifying questions. You will want to state them later as your part of your edge cases, but you always want to note these. Anything that your interviewer replies with, you want to add your notes right below the answer, or the reply from the interviewer. All right, so let's think about some edge cases. So this is where you can take some of the edge cases you found from clarifying questions, right? Duplicate, uppercase and lowercase, empty string. All right. And not only that, but try to think of any other edge cases, right? There's some edge cases where potentially it could be one character in a string, right? Or it can be 100 characters of all unique characters, right? These are just some of the cases that can happen. Once you feel like you've defined your question, and if you don't feel like you clearly defined your question yet, make sure to communicate that with the interviewer. What are you unclear about? It's really important that you define the problem for yourself, right? Because the next step is going to require you to build some test cases. And to build some test cases without understanding the problem, you'll have a very, very tough time building any test cases. So here's my test casing phase. So let us assume that we have an S string containing A, B, C, D, E, F, and the expected outputs should be, and let's see. So AB, this would be considered a unique substring. A, B, C, D, E, F, that would be considered a substring without duplicate characters. It's actually probably the largest, right? I think if we look at any of these following characters, you just simply get smaller and smaller in terms of size. So let's assume that Actually, we don't even have to assume. We can confirm that A, B, C, D, E, F is going to be our expected output. So it'll be the length of that substring, which is 6. So while you're building the test case, take a note how you found out this was the substring without duplicate characters. And do it step by step, because oftentimes how you visually solve it will end up in either a brute force case scenario, or it can even land you the optimal solution. Take it one step at a time. Analyze how you are inferring the answer. So in my case, right, I'm checking the A, I'm checking the B, looks good so far. Then I check the A, and I realized that I had an A at this position. So because of that, I'm going to reset and put it at B. BA is still unique, right? Then we find a B here. We're going to do the same thing. We're going to want to move this up because we want to make sure that we're always getting a unique substring. So we're going back to A. Then we'll want to check all of these characters. And we reach the end. Do we need to check these characters? No, it's not necessary. So we can end here once you reach the end of the string. So this is one of the test cases. Then you want to try out some of the test cases with your edge cases. So we have 4 edge cases here, and I'll just take out this edge case of 100 character with unique input. We can expect the output just be the total length of S, but let's write out some test cases to match your edge cases. This is important. This gives you some intuition on how you're going to handle the edge case. So our first edge case, uppercase and lowercase. And I'm going to just put a random set of characters. Maybe a more simpler prompt for us to go through. Just for the sake of time, right? You wouldn't want to go too crazy on the test cases because you have to realize that you are under time pressure. So here's an input with both uppercase, lowercase, and special characters with numbers. And we can even put a space in there. What would our expected output be? Our expected outputs, and if we follow the same algorithm, A, B, A, and we're accounting that uppercase and lowercase will be considered unique, C, 2, 1, 5, pounds, space, and percentage. So in this expected output, we can say that this length, this output, would be equal to s dot length, which is the total amount of characters that lies within the string. So this is 9 characters. And we can do the same for an empty string. Expected outputs, unknown. If there is an empty string, do you want me to output something different? You have to ask that question, right? Are there special output case for this? And then for S of 1 character, and that is pretty intuitive, this expected output is simply s.length or 1. So we've defined a problem very clearly in 15 minutes. This is a medium problem. So because you've clearly defined your problem, you should be able to have a better path to constructing a solution, whether that's brute force or optimal. So I'd give you about five minutes to construct a brute force approach, and then we will continue the video from there. So hopefully you were able to find the solution. If not, that's okay. We're going to go through it together. So let's start with the brute force approach. I'm going to take one of our examples here, B, C, D, F, and we're going to tackle this together. So the brute force approach, right, would be simply to find each substring, every single substring within the string itself. So we can find AB, move it up, BA, AB, ABC, ABCD, ABCDE, F, move this up, and do the same process over and over again. We're checking each substring. This would be in the form of a nested for loop to accomplish this. But it is a valid solution for brute force, right? Now, the question is, how can we optimize this? Let me show you where you can infer some potential optimization. So notice when we ran through the nested for loop algorithm, that even though that this was the longest substring, we continue to check each and every one of the substrings of our answer. Question is, did we have to go through all of these substrings, or is there a way that we could have just simply stopped here? Right? Or in another case, could we have just simply, once we found this substring, once we saw F, we just moved this forward, and once we reached the end, we stopped, right? Instead of checking every single combination, you can ask yourself this question: is or was that necessary in the brute force algorithm? So now we're going to dive into the optimal solution, and I hope the brute force solution was intuitive for you. But moving on to the optimal solution. So I actually liked when we had this window here. So we start off here, right? Let's just say at the very beginning of our algorithm, we start off here. This expands to A, then expands to B. What happens when we expand to another A? We find our first duplicate. So we can put some sort of star here. So we find our first duplicate. The question is, what do you do when you find your first duplicate, right? And at what position would that duplicate be? So ABA, and notice how we move this up to B. Okay. we can do the same thing over here when we move this to the B. You're going to notice that we're going to move this pointer up to the A. And we're going to move this up. So this goes up, this goes up. We see an F. Oops. I'm going to detach this arrow. So we see this F. We go through this algorithm as well. Then when we hit the next F, watch what we do. We move, our pointer is here, right? And now we have another duplicate spot. We can almost forget about this because that was in the past, right? We want to make sure our window is moving forward. But watch how our window changes like this. This was the duplicate F. And then we can move forward. So this is a typical sliding window problem, but as far as the solution goes, you can see that we want to keep track of each letter, right? We want to keep track of the position of each letter. That way, when we do find the duplicate, we want to move our starting point one above or one forward in front of the duplicate. That way we can make sure our substring, our window is always going to be a substring without duplicate characters and a substring that will keep on moving forward. Right? Because there's no need for it to go back to find another substring. Let's say we're all the way here, right? FA. Is there any necessity to go anywhere farther than that F? Right? Because as soon as it goes one more farther than that F, it's already no longer a duplicate. So that's why we're always moving forward. Right? So let's start there. We have our A, and let's say we have our B. We're always keeping track of every single location for the characters. We're keeping track of their indices. So A, B, A. So we start with the A, we move on to the B. When we see the A, we find the last seen A's indices, and we move it up one. That's going to be the new start for our window. All right. Then this is our checking arrow. We call this the check arrow, because this can be representing the start of our window, and our window will grow in size with this arrow. We see the B. Then we find the position of the oldest B inside of the substring. It doesn't make sense if the B is all the way back here, right? Because this window cannot go farther back, all the way back there. As soon as it moves here, it's invalid, right? Because we already checked. There's already an A in this substring. We cannot go back. So just like in the previous example where we had the ABA, this will be moved up because the oldest B that we found inside of our substring was at position indices 1 or position 2. And we will move this +1 and adjust our start. And we would do this same algorithm over and over again, right? Until we hit the next duplicate. Then it would be rinse and repeats, right? So this would move up. And this is actually a unique scenario, right? Because both are starting and pointing actually reset again because the F and the duplicate F are right next to each other. So it actually starts here again. And we continue our algorithm. So that'll conclude this video. I'll post my C# solution below in the description, but obviously make sure to try this out in your own coding language and in your preferred coding editor, whether that's going to be in LeetCode or if you want to tackle this in VS Code or Visual Studio Community. That is up to you. And if you want to post your solution in the description or in the comments below, feel free to. Otherwise, uh, if you're looking for any solutions, you can find them in the LeetCode question, and I'll put that in the description below as well.